Thank you, Raymond. So I'm basically continuing the topic which has been introduced by Graham in the previous talk, and I'm going to look at understanding complex cloud systems using complex and more idealized models. And I've worked on this with Graham and Franziska, who's also giving a talk later today. So first of all, I would say that our community made enormous progress in the last years to model atmospheric clouds. So we have really developed great microphysical tools to represent all the little interactions of aerosols, cloud droplets, and rain droplets on a really huge range of scales using, for example, the super droplet methods, which Anna introduced earlier, or bin models, which also have been around for several decades. And we have also developed quite nice fluid dynamical models, for example, large eddy simulations, which can be used to represent entire clouds, cloud fields, and even the little entrainment events going on the cloud. And with this, we can today basically represent clouds and cloudy systems on a range of scale between 1 micron up to 100 kilometers. This is not perfect, but we are pretty good in representing this range of scales. However, we somehow tend to only model certain cases. So there are specific cases which Anna also touched upon in the literature, which are simulated all over and over again. For my talk, of primary importance are straticumulus cases, and there are two rather idealized cases which are usually used. There's this non-precipitating closed cell straticumulus case based on the DICOMS 2 campaign and the research flight 1, which is something like this here in the red square. And then we have also open cell straticumulus cases, also based on the DICOMS 2 campaign, but the second research flight of that campaign, which is some kind of cloud system which is shown here. And these cases are great. We can learn a lot of them. We can learn how the cloud physics react and how they are sensitive to certain microphysical assumptions that we make, but they only represent a certain or a limited range of the entire phase space. And we, for example, don't know what is going on here. So we don't cover this. So in my talk, I'm going to talk about how we can use huge ensembles of large eddy simulations to understand cloud microphysics in a slightly broader and larger phase space. But first of all, I would like to remind you what Graham has already told you about how these closed and open cell straticumulus work and behave, because this is quite important for the following talk. Straticumulus are very important for the climate system. They cover around 20% of the globe, and they're very important negative forcing in the radiative budget because they reflect a lot of light, shortwave radiation back to space. But they exist in two distinct states. First of all, we have these closed cell straticumulus, and they're mostly driven by long-wave radiative cooling from the cloud top, and this creates a somewhat Rayleigh-Bernard type circulation with relatively broad updrafts with a lot of cloud on top of it, and quite narrow downdrafts on the edges of these cells we have also heard a little bit about today. On the other hand side, we have open cell straticumulus, and they have typically not a full cloud cover, because here we have, as Graham already explained, downdrafts in which we have evaporating rain causing cold pools that cause convergence with relatively narrow updrafts and relatively narrow clouds and relatively broad downdraft regions, and that's why we call them open cells, because these downdraft regions are typically cloud-free. And when we switch from closed cell to open cells or backwards, this has enormous implications for the Earth radiation budget, because these open cells, we don't have any cloud cover here, and we have the ocean, which absorbs then a lot of incoming shortwave radiation. So, and for straticumulus, we found, for example, in satellite observations by Engström, that there's a really nicely constrained relationship between the seen albedo and the cloud fraction, which you can see here on the right. So the cloud fraction is basically the fraction of surface area covered by the cloud, and the seen albedo is given basically by this relationship, which is proportional to the cloud albedo, so the albedo of the individual clouds times the cloud fraction Fc, and the surface albedo, which you can usually assume is constant, and which It's typically much, much smaller than the cloud albedo. And if the cloud albedo would be constant, then we would see a linear relationship in this nice phase diagram. But we can see here that this relationship is not linear. It's more or less superlinear. And there are several explanations and hypotheses why this relationship is superlinear. Some people say it's due to increasing cloud droplet concentrations, which would make the clouds more reflective here at higher cloud fraction. It could also be due to deeper clouds at high cloud fraction, which would also cause a higher cloud albedo and therefore this superlinear increase of the scene albedo. And to understand this a little bit better, we created an ensemble of 127 large eddy simulations of stratocumulus top boundary layers, where we varied basically 6 parameters in this ensemble, which is basically the temperature of the boundary layer, the humidity, the jumps of humidity and temperature from the boundary layer to the free troposphere above. Then we varied the boundary layer depth, and we also changed or varied the aerosol concentration. And then we had a 48 by 48 square kilometers domain and simulated these simulations for 12 hours basically. And the cloud microphysics are represented with a bin emulating bike scheme. And you can see here these worms, which we have talked about earlier, they represent all the different simulations we've conducted, and they all nicely more or less follow that angstrom line, which has been determined from satellite observations. So this is quite great, but we want to understand this a little bit better. So we started to separate these individual runs into precipitating and non-precipitating runs. So we have seen before that the precipitating runs tend to form these open cell stratocumulus structures. The non-precipitating runs form these closed cells, and still, the precipitating runs are more or less basically dominated by the transition from the full cloud cover to the low cloud cover, because we form these open cells, while the non-precipitating runs do exactly the opposite. They go from the open cell state to a closed cell state. And as I said before, we separated these runs by the surface, the cloud-based rain rate of these cases, and we can see there's a nice separation in between the cases. So if you say that we have a cloud-based rain rate of about 1 millimeter per day, we get these precipitating cases, and all the other cases which have a cloud-based rain rate of less than 1 millimeter per day are considered as non-precipitating. And it's actually in itself quite interesting that you can separate the entire ensemble of simulation which we have in these two states. There's only one simulation of these 127 which is doing something weird, which is going between these two states, and we neglected it here in the analysis. Right, the cloud fraction. So, and you can see here that especially the non-precipitating cases, we have a almost perfect agreement with these observational determined angstrom line, that superlinear behavior. And in the precipitating cases, we lie slightly above that angstrom line, and we have a slightly stronger increase for higher cloud fraction. And now we want to understand this a little bit better, and we start with the non-precipitating stratocumulus. So here we see the cloud albedo in this cloud fraction scene albedo phase space, and we can see quite nicely that for higher cloud fractions and higher scene albedos, we see an increasing cloud albedo, which makes sense because we need this to get this superlinear increase in the scene albedo. And because the cloud albedo is basically proportional to the number concentration of cloud droplets times the liquid water path, basically the vertically integrated liquid water, we can see if this change is due to microphysics or more or less the macrophysics, the changes in the liquid water path. And we can see no real clear signal in the number concentration. But we see a pretty clear signal in the liquid water path, because it basically increases when we go to higher cloud fractions, and therefore this change in the liquid water path is mostly responsible for that superlinear behavior. And to understand this a little bit better, we took the temporal derivative of the scene albedo, which is basically composed of the temporal derivative of, or the temporal change in the cloud cover and the temporal change in the cloud albedo. So here you can see the temporal change in the scene albedo, and we can see here a nice peak in the scene albedo for intermediate values of the cloud fraction. And you can see this nicely coincides with the temporal changes in the cloud fraction. So the changes in the scene albedo are mostly driven by the changes in the cloud fraction. However, and as I said before, changes in cloud fraction cannot only explain the changes in the scene albedo, we also need changes in the cloud albedo, which we can see here. And we see here a slight positive trend in the cloud albedo starting at about 0.5 cloud fraction up to 1. And we also see this quite nicely in the liquid water path here on the right-hand side. And to understand this a little bit better, we used a mixed layer model. A mixed layer model is a really simplified representation of what is happening in a boundary layer. And this has been developed by Doug Lilly in the 1960s already. And it basically budgets the different fluxes into the boundary layer. So we have the entrainment fluxes at the cloud top. So we have, for example, the entrainment of free tropospheric air, which is usually removing cloud or evaporating cloud. And then we have also the possibility that the entrainment raises the cloud top because it allows deeper clouds, which could increase the liquid water path in the cloud. And we have precipitation, removing liquid water from the system, and we have surface fluxes, and of course we have long wave radiative cooling. And by looking at this mixed layer model, we can determine a framework or develop a framework in which we can understand the liquid water path changes in our LES ensemble. And this is what I'm showing you here. So again, we have here the cloud cover and here the temporal changes in the liquid water path. And here you can see all the different contributions to the liquid water path budget. So first of all, we can see that we have no precipitation, which is obvious because these are the non-precipitating cases. We also see that the surface fluxes almost do not contribute to the liquid water path budget in this case. It's a little bit more interesting when we look at the cloud top entrainment contributions. So we can see that first of all, cloud top entrainment decreases the liquid water path because we entrain warm and dry air from the free troposphere, which is evaporating the cloud. But we have a slight positive contribution due to the upward motion of the cloud top, allowing slightly deeper clouds. So overall, we have a slightly negative impact of these two cloud top entrainment related processes. Last but not least, we have the radiative cooling, which is the most important term here, and it's the most major liquid water path source for these clouds. So if we budget all these cases together, we can see that the mixed layer model tendency is positive throughout the entire FC space. And this is somewhat contrary to what we've seen in the LES simulations before, because in the LES, we have seen that we only have positive tendencies here around or above 0.5. So what's the problem? So we can see that we have a nice, interesting agreement of the LESs with the mixed layer model for a cloud fraction of 1. This is great, this is working. But what is happening below a cloud fraction of 1? And this is basically the lateral entrainment. We need to produce liquid water, basically, which is then spread out to increase the cloud fraction of these clouds. And you can basically diagnose this tendency from the temporal changes in the cloud fraction and get this term, and this approximately closes the budget. So to get this mixed layer model right, we need to add the lateral entrainment tendencies to close the entire budget. So to conclude this intermediate result, we can say that we need to understand the basically the interplay of radiative cooling and lateral entrainment to understand the liquid water path increase of the non-precipitating stratocumulus. And here's some little interesting feature which we also found in our LESs. because, as I said before, the lateral entrainment is driven by the temporal change in the cloud fraction, which you can see here in the black line. If you go back to the really old literature on entrainment and retrainment, you can basically theoretically calculate how this change should look like. Based on Turner, you can basically show that the temporal change in cloud fraction should be proportional to the cloud fraction over the typical cloud radius, which we determined using Fourier analysis, which you can see here. By combining these terms, we almost match what is happening in our LES simulation, which is, I think, not that important, but a pretty nice feature and shows how well this theory works and also how well our LES simulations capture these behaviors. Last but not least, I would like to briefly talk about the precipitating clouds, so which basically go from a closed cell state to an open cell state. And here we only look at the temporal changes in the scene albedo, and we see that it's negative throughout the entire FC space, and it's mostly driven by the decrease in the cloud fraction, as we have seen before. And what you would expect is also a strong impact on the cloud albedo, because we have strong rain, which is removing liquid water, which is removing cloud droplets, which you can see here in the cloud albedo. But the cloud albedo is only negative for values above 0.8, and it's basically 0 below that. So that was a little bit baffling, so we wanted to understand this a little bit better. And to understand this a little bit better, we were basically creating a budget of the changes in the cloud albedo. And the changes in the cloud albedo are determined by the changes in the liquid water path and the droplet number concentration. And if you do this, we can see what we have expected, that the changes in the number concentration are negative throughout the entire FC state, which makes sense because we have precipitation all over the state space, and precipitation is always removing particles. In the liquid water path, we have only a negative tendency for values above 0.8, which is the liquid water which is removed by precipitation. Below 0.8, we have precipitation and this organization of the cloud field, which allows individually deeper clouds, and deeper clouds usually have a higher liquid water path, which explains this increase here. And if you combine these two tendencies, you get a very negative tendency here and an almost zero tendency below 0.8, which is then also explaining why we have that almost linear behavior, which we have seen in the beginning for the precipitating stratocumulus. It's summarized here. So, and with this, I like to basically conclude my talk. So we try to understand the relationship between scene albedo and cloud fraction for stratocumulus transitioning between open and closed cell states and vice versa. For this, we use an ensemble of 127 large eddy simulations, separated in precipitating and non-precipitating simulations. And for the non-precipitating simulations, we have shown that they follow the known superlinear relationship from Engström. And with mixed layer theory, we have explained this is mostly caused by the balance between radiative cooling and lateral expansion of clouds, which is then determining the increases or changes in liquid water path. For the precipitating stratocumulus, we have shown that the results lie slightly above the observed AFC relationship, and it exhibits a slightly more linear behavior for intermediate cloud fractions. And we have generally higher liquid water path for a given cloud fraction because the clouds are basically contain a little bit more liquid water than in the non-precipitating case. And at high cloud cover, we have strong losses in the droplet concentration and liquid water path through precipitation, which cause a decrease in AC. And at low cloud cover, precipitation losses are balanced by deeper clouds, causing an almost constant cloud albedo and hence a linear decrease in A. So, and with this, I'm done. Thank you very much.
Okay, we'll take questions for Fabian.
Yeah, Steve. So I'm used to thinking of lateral entrainment in cumulus cloud. So could you explain the physical meaning of this lateral entrainment in stratocumulus? It's broken stratocumulus, so I think I know what you mean, but.
Yes, I mean, it's quite, in the end, it's quite relatively similar to what is happening in cumulus. So in one of the first slides, you see there's basically towers. So they have lateral edges and then basically detrain liquid water to the edges, which is increasing than the cloud fraction. Furthermore, you have to consider that we have a slightly more stable stratification on top of these clouds. I mean, cumulus clouds are just basically penetrating into the free troposphere. Here we have a slightly more stable atmosphere. This also causes some divergence at the cloud top, which is also contributing to this effect.
Did you have a comment?
Yeah, this is really interesting. I look at it from a completely naive standpoint, I guess. So to me, albedo is something to do with radiation, and the FFC is a geometrical aspect ratio or geometrical variable, and I can buy it that the drops will behave differently than clouds or ice particles and such. So why bring in the fluid mechanics? Why is the LES telling us anything about radiation versus geometry?
Because we somehow need to represent the mesoscale organization, because we need to understand these transitions and how these cloud fields are created. I mean, one could do all these calculations probably by just assuming something. But you've seen also in Graham's talk and Francisca's talk later on, this mesoscale organization of cloud fields is quite important. We have these distinct differences between open and closed cell clouds, and we need to understand these transitions. So, I mean, in the end, we probably could use like this Engström line to parameterize everything. But I mean, my work was basically, or my intent was to understand what is causing this nice behavior. I mean, we could use this, but it's always nice to understand why we have this curve. And this was the main intent of this.
Maybe if I could just ask a quick question. I was surprised, maybe it's related to this point, I was surprised at how similar the lines are for open and closed cells. I mean, if you would have asked me to make a guess, I would have said high cloud fraction is closed cells, low cloud fraction. Can you show that plot again? You had, I think, 2 lines, and they were surprisingly...
I mean, I think these were these two. I mean, this is non-precipitating.
Yeah, I guess, but right. So, but the point is, you can apparently reach cloud fraction of 1 with precipitating clouds, which
right.
is.
But it will stop in the end eventually.
I see.
I mean, it's not. It's. I mean, it.
So maybe it's a transient.
It's basically the initial state which we have, and then it moves away quite quickly.
I see.
So I mean, in regard to the question that's just not the one that Ray, but before, why would you have to do LES or something like that? I mean, if you're really thinking about influencing these type of clouds in any way, any intervention will be local. You will not be able to globally change the radiation of the sun. You will have to do value. It will always be local, even if you put a mirror up there that shines on the clouds. So if you think about climate engineering in any type, you will not get around the LES. Or some fluid dynamic simulation, you just can't, because you will have to talk to all these patterns, and so I think that's why the global aspect is nice, but the local aspect will just be important. And Ray asked me, when was it, 2 days ago, whether I think this type of climate engineering will happen. I've been saying this for many years now, that we will be forced to do it as soon as our civilization is going down the drain. Because all of Bangladesh is coming to Germany, then I can tell you something will happen, or to the US. We will do everything to avoid that whole countries will drown in water and will suddenly try to. I mean, it could really be, I mean, this kind of political impact of this climate change is going to be the worst, which we, in my opinion, are not foreseeing right now, and we have no international laws that talk about clouds, none. There's no agreement of who owns a cloud, who has influence on weather, who's allowed to change the weather. I mean, there's nothing whatsoever. And I can only basically speak to the people that are here and the world. I mean, we should really sit together and think about, do we need it? Should we not make at the UN level really talk about this? I mean, there's always rogue states, but let them leave rogue. It worked for stem cell research, worked very well. And for gene-modified food and all that stuff, it worked. So why not think about climate engineering in the broad sense and make some international laws and agreements that are sensible and guided by science and not by needs? Just a little. So sorry.
It just
was a bit philosophical. Thank you.
Much more philosophical here. Any other additional questions? Or yes, yes, please.
So I feel this is so dull compared with climate change, but I'm going to be brave and ask it anyway. I was trying to understand the distinction, the thing that you're calling the cloud albedo. I think that's AC, right?
Yes.
And how localized do you effectively calculate that? I mean, I could imagine, so there's the seen albedo, that's kind of the average area where the cloud is existing, right? And then the cloud albedo, I could imagine in a region where there's a lot of droplets being different when there's maybe just more tiny droplets, I guess, the ones that are getting close to it. And so that's my first question, is how different is that? Can you comment on that?
I mean, the cloud albedo is basically determined locally for each individual cloud.
Okay.
So we have the entire scene, and then we basically look for certain regions of the scene which are above a certain threshold. We usually use the optical depth, and the optical depth is basically a metric to show where we have a cloud or not. And when we have a cloud, we calculate the cloud albedo, and it's basically proportional to the number of cloud droplets in the liquid water part.
Okay. So that's interesting. I'm also wondering, it seems like there's just 1 point per scene that's AC. Am I imagining that? No. Because a lot of times
there is some variability between the individual clouds which we have, or I mean for the entire cloud field.
But what you're plotting tends to be for the whole cloud field, where there is a cloud. Like you said, you calculated for each cloud, AC. Do you calculate one AC per scene?
I see. I mean, it's the average AC for the entire cloud field, but all the individual clouds go inside this calculation.
Okay. And then if I could ask one more little question, so the worms in different ways have been emphasized, but you said here these are worms like Graham showed, and I'm wondering just if there's physical significance. To me, I would say, okay, that has a slightly different initial condition, so of course it's different and it squiggles around a little bit. Like that's how I would see it in the systems that I look at. But is there actually a significance and maybe some sort of dimensionality to the curve that's interesting, or is it just a descriptor that you're using?
I mean, the curves which we see here, I mean, this is basically...
But that doesn't show the worms, right? Like you said, okay, here's worms like what Graham showed. Yes. Is there significance to calling it a worm, or is it just like squiggly line that sounds slightly more sophisticated?
Line is basically the average of all the worms which we have. So this shows the average worm behavior.
Okay.
So there is some wiggling of the worms around that average behavior, and you can see look at the simulations and make some detailed analysis why they wiggle up or wiggle down. Mm-hmm. That might be something which is happening, but here you can see the mean behavior going from high cloud cover to low cloud cover and vice versa.
Okay, but in general, like this is not something that is so significant for the type of modeling that you're doing. That and again, it's sort of an averaging that you take over it. Okay, thank you so much.
Okay, let's thank Fabian and all of our speakers.
Sorry, there's one more person in line that was waiting.
Oh, okay. If it's a quick question,
Just thank you. A quick question from someone outside the field. How did you choose the different the 127 markets? How did you choose the temperature and these parameters? So we first started with a realistic range of parameters for all these variables, and then we used Latin hypercube sampling, so which is a statistical approach to build up this ensemble. Okay, thank you.
Okay, thanks. Let's say thank you, and we'll break.